So now I'm going to talk to you about something called nuclide notation. Do you see that when we name those isotopes, like carbon-12 and carbon-14, it's a -14, and students oftentimes get that confused with the charge, and then they start to mess around with the electrons, and you just don't want to do that. So we're going to show you a way to show the symbols of an element and the symbols of two different isotopes using a notation known as nuclide notation. It includes, again, the mass, it includes the atomic number, it includes the symbol of the element, but it has to go in just the right spot in order to be able to use it. So I'm going to show you how this works. Now let's say I want to write out the nuclide notation for the most common isotope of fluorine, which is fluorine with a mass of 19. So the way I do this is first I start with the symbol for fluorine, which is just a capital F. And now I figure out what the atomic number of fluorine is. And the atomic number always goes in the lower left-hand corner of the symbol. Imagine the symbol is surrounded by an imaginary box. I drew the box in, so it's less imaginary now, but we don't draw the box in when we actually do the notation. But I will use the box to show you the placement of the numbers. Now in the lower left-hand corner of the box, you'll put the atomic number. And since fluorine is atomic number 9, we're going to put 9 down here to represent the number of protons. Now in the upper left-hand corner, we put the mass of the isotope. And I identified the mass of the isotope in the name, fluorine with a mass of 19. So we're going to put a 19 up here. Now if this was a charged ion, we would put the charge of the ion up here in the upper right-hand corner. But this is neutral, so you can just simply leave it blank. Now if I get rid of the box and I have just the numbers and the symbols, here's what it looks like. And now you have the nuclide notation for fluorine with a mass of 19 and the atomic number as 9. Nuclide notation is really useful for us as chemists because it helps us identify the element, the element's atomic number, and by using the mass and the atomic number together, we could easily subtract these two to figure out how many neutrons this has. So let's do that. 19 minus 9 is 10, so this fluorine has 10 neutrons. There are a couple of different ways that nuclide notation can be used to ask questions on homework or quizzes or tests. Typically, what you'll see is one of two types of questions. The first type of question is if I give you the nuclide notation and I could ask you some key information about that substance. For example, I could give you this notation. So the symbol is O, and we know that's oxygen, and you can confirm that by checking the atomic number of 8. That is the atomic number for oxygen, which represents the number of protons. So if I say, how many protons, neutrons, and electrons does this isotope of oxygen have? Well, you can say, okay, well, its atomic number is 8, so I can put in an 8 for 8 number of protons. And I see that it isn't charged. There's no number here in the upper right-hand corner, and so I know that the number of protons and the number of electrons are identical, so I'm going to also call that number 8. And finally, what I can do is I can do a quick subtraction because I know that the mass minus the protons equals the number of neutrons, which this also happens to be 8. So with just the nuclide notation, I can identify the protons, the neutrons, and the electrons of any isotope. Now you probably expect the other thing that I could do is take the key information and ask you to draw me the nuclide notation, making sure that the numbers are located in the proper spots around the symbol. So let's start with some key information. I say you have got a particle with 11 protons, 12 neutrons, and 11 electrons. Tell me what the nuclide notation is for this substance. First thing you want to do is take a close look at the number of protons. There's only one element on the periodic table with 11 protons, and that substance is sodium. So I put the symbol Na for sodium in the middle. And now I can put the atomic number in the lower left-hand corner. The next thing I want to do is check to make sure that the protons and the electrons are equal, and they are. So I don't have to worry about putting a charge here in the upper right-hand corner. I can just leave it blank. And the last thing I want to do is figure out what the mass of this isotope of sodium is. And since I know it has 12 neutrons and 11 protons, if I add those together, I get a mass number of 23. And now I have successfully identified the nuclide notation for this substance with 11 protons, 12 neutrons, and 11 electrons. Now, in order to understand what I'm about to tell you, it's important that you have done the build an atom activity that we did last week. But a stable nucleus is one where it has just the right amount of neutrons in the nucleus. If a particular nucleus doesn't have enough neutrons, or if it has too many neutrons, it will become unstable. And an unstable nucleus is not a good one it's going to either try and fuse with another nucleus or go through fission in order to create a more stable nucleus. In summary, the identity of an atom depends on the protons, but the stability of an atom depends on having just the right amount of neutrons in that nucleus. This is why we talked about isotopes in a previous video lesson, because isotopes aren't always stable. Just because they exist doesn't mean they stay that way forever. Some isotopes are much more stable than others. Let's quickly talk about the goal of a nucleus. What is it really trying to achieve? Just like human beings, nuclei, which is the plural of nucleus, nuclei are just trying to become stable. Just like humans are trying to find a nice, comfortable spot in their life where they are happy as can be, mentally and physically. But unlike nuclei, humans don't have an exact moment of stability. Our stability as humans is fluid. It changes from moment to moment. They don't know exactly when they're stable, but when it comes to a nucleus, there is a stable moment. And that stable moment is when they reach the nucleus of iron. Iron has a nucleus of 26 protons and 30 neutrons. For rules that I'm not able to explain to you in this class, iron is the most stable nucleus that can be achieved by fusion or by fission. Let's first talk about the definition of fusion. The basic definition is where two small nuclei combine to make one larger nucleus. The most basic form of fusion happens in our sun and all stars, where elemental hydrogen combine to form helium atoms. Now, if you're doing the math and you're looking at this, you can see where the proton from one hydrogen and the proton from another hydrogen combine to form the protons for helium. But the mass of helium is 4. Now, elemental hydrogen has no neutrons. And so where do the neutrons come from to make elemental helium? Well, neutrons exist, and they don't need to necessarily be combined with another nucleus. They just kind of hang out in the sun. The sun is more of a soup of elements and neutrons and protons just floating around. And if you get the temperatures really hot and you get the pressures very, very high, these hydrogen atoms and some loose neutrons combine to form helium in just the right combination. So if I were to more accurately draw these nuclide notations for hydrogen combining to make helium, I would have to include some neutrons as well. The notation for a neutron is just a lowercase n, but it doesn't have an atomic number. Its atomic number is 0, but it does add 1 to the mass. Now if you're doing the math, 2 of the neutrons plus 1 equals 4. And so the top numbers all add up to equal 4, and the bottom numbers all add up to equal 2. And now we have the right amount of protons and the right amount of neutrons and the right mass of the nucleus for helium. And when those atoms combine to form a new nucleus, a lot of energy is released, which is how the sun is able to produce heat and light that can allow for life to form on our planet. But reaching the nucleus of iron doesn't happen in one single step. Rather, it happens in incremental steps when smaller nuclei combine to form a little bit larger. And that little bit larger nucleus combines with another small nuclei to get a little bit bigger yet. And that process repeats itself till eventually the nucleus gains 26 protons and 30 neutrons. And at that point, it will stop going through fusion. Fusion's goal is to combine small nuclei to create larger ones and eventually reach the stopping point of the iron's nucleus. Fission, on the other hand, is the opposite of fusion. It's the splitting up of an unstable nucleus in order to achieve a more stable state. Fission is what's happening in nuclear reactors to produce energy by taking large unstable nuclei and splitting them up into smaller, more stable nuclei, and as a result, it also releases energy. But what makes this different than fusion is that fusion requires temperatures of nearly 40 million degrees in order for fusion to occur. But fission can occur at relatively low temperatures, and so this process can be done in a controlled environment in a nuclear reactor. The concept behind fission is that you take a very large nucleus, much, much larger than iron, and it splits up into a little bit smaller nucleus and usually a very small nucleus like that of helium. This process then repeats itself, where the slightly smaller nucleus then splits up into two more nuclei, one of which is smaller than the original. We call this the parent nucleus, and then the two daughters as a result, one of which is helium and the other is a little bit smaller than the parent. And then this process continues until eventually the final nucleus is that of iron with 26 protons and 30 neutrons. I'm going to show you now one of the most common nuclear reactions that is produced in a nuclear reactor, and it requires the use of uranium, which is a very, very large and radioactive element. Uranium, with a mass of 238 and a number of protons of 92, splits up into thorium with a mass of 234 and an atomic number of 90, and a helium atom. Notice once again the atomic numbers down here, the bottom numbers, 92 splits up into 90 plus 2, so we don't lose any protons. And the mass, which represents the number of protons plus neutrons together in the nucleus, goes from 238 down to 234 plus 4. So the top numbers add up together and equal. We've got 238 on this side, and these add together to make 238. We got 92 on the left and 90 plus 2, or 92 on the right. And like fusion, the result of this nuclear decay, as we call it, or a fission of the nucleus, also results in the release of a lot of heat. Well, that takes care of this video lesson. Thanks for watching.